When we perform chemical reactions in the laboratory, we need a way to get from the microscopic to the macroscopic. That is, from properties that we can measure like mass and volume, and relate that to how many particles are actually involved. And we need to know that because we write chemical reaction in terms of the particles involved. Here's our chemical reaction. H2 plus O2 goes to H2O. And it's 2 particles of hydrogen and 1 particle of oxygen to give me 2 particles of water. But I can't go into the stockroom and say, give me 2 particles of hydrogen and a particle of oxygen. I need to tell them, give me a gram or 10 grams or 3 liters. What's the relationship between that microscopic and macroscopic property? Well, it turns out it's pretty easy. We just scale up from the relative masses. From the relative masses of the individual particles, we scale up to masses that we can measure. For instance, if we know oxygen has 16 times the mass of hydrogen, then if they're going to react 1 to 1, the mass ratio will always be 16 to 1. That is, 16 grams of oxygen will react with 1 gram of hydrogen and have the same number of particles. It's as if you were going to go to a hardware store and you wanted 500 nuts and bolts. Now, no one wants to count out 500 bolts, but the guy at the hardware store might say, oh, the bolts weigh a gram, so weigh out 500 grams. That'll give you your 500 bolts. And you say, but I also need the nuts. And he say, oh, the nuts are half as heavy. They have half the mass. Well, then weigh out 250 grams of bolts, half that mass, and you'll be assured you have a nut for every bolt. You've used the relative mass to match up 1 to 1 nuts and bolts. That's how we do it in chemistry. We take one element to be the standard. Carbon will be the standard, and I'll measure all my relative masses relative to carbon-12. So I'll take 12 grams of carbon-12 to be my standard mass. Now, hydrogen weighs 1/12 what carbon weighs. So if I take 12 grams of carbon-12, I would react it with 1 gram of hydrogen atoms, and that would be a 1-to-1 ratio. Or 24 grams of carbon-12 with 2 grams of hydrogen. That would still have a 1-to-1 particle ratio. Now, it's not 1-to-1 particles. How many particles are actually in that 12 grams of carbon-12? Turns out it's an astronomically large number. Avogadro's constant. 6.02 times 10 to the 23rd particles, that's 6 and 23 zeros after it, is the number of particles in 12 grams of carbon-12. Since hydrogen atoms are 1/12 the mass, 6.02 times 10 to the 23rd hydrogen particles will have a mass of 1 gram, 1/12 that mass. So I can match up hydrogen and carbon in that ratio, 12 to 1. I'll give this unit we're talking about, 12 grams of carbon-12, a special name, the mole. So 6.02 times 10 to the 23rd particles of anything, carbon, hydrogen, oxygen, will be a mole of that thing, carbon, hydrogen, or oxygen. So a mole of carbon-12 particles is 6.02 times 10 to the 23rd, and that has a mass of 12 grams. So the units we'll use are 12 grams per mole of carbon is a mole of carbon. So that's how we're going to make the connection between macroscopic properties and microscopic properties. We're going to use Avogadro's constant and our concept of the mole.